Page 2 now of 7.4. Again, we're calling this 7.4 most. We're covering most of section 4 right now. We'll come back and get the leftovers after we do a little bit more factoring. On page 438 gives you the difference of squares formula, one of the two patterns or three formulas, however you want to look at it, that you'll need to memorize when facing two terms that need to be factored. And on page 439, a study tip, it's helpful to recognize perfect squares. So here's the perfect squares from 1 to 16. You might, and this would be a good list to just be familiar with, not necessarily memorize, but being able to recognize that 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256 are perfect squares. It saves you precious minutes on a test, and then there'll be a list of some cubes that you should be familiar with too later on as we go through. You might even get familiar with 17 squared, 18 squared, 19 squared, 20 squared, not as often seen, but if these are getting pretty familiar to you, 20 squared is 400, 19 squared is going to be 361, not seen as often. Really, this first 16 will get you to where you need to go. If you see 324, that's the same as 18 squared. If you see if you see 289, that's 17 squared. 324 is 18 squared. So this is just a good list for you to recognize. Just be aware of these, review these every couple of days or so, or maybe once a day. That way when you see them on the test, you don't have to wonder, is that a perfect square, a perfect cube? You recognize it, and it just gets you right away to which formula to use. So moving down the page to the rest of these examples here, what if they looked like what we see here on number 32 from page 444? What do you have x squared plus 4? Again, we're going to get really boringly good at factoring. We ask ourselves, is there a GCF? Is there something both terms have in common? The plus is what helps separate the terms. There's no GCF here. The second question we ask is, how many terms are we dealing with? Boring, boring, boring question at this point, because all we're looking at so far is two terms, but very soon we'll start to see more. And they'll be mixed up too, so very important question. In this case 2, which means it has to fit one of these situations to be factorable further. It has to either be a difference of squares, a difference of cubes, a sum of cubes, and remember that a sum of squares, there is no formula for that. And in this case, that is what we have. We have x squared is x times x, 4 is 2 times 2, so those are perfect squares. Both the 4 and the x squared are perfect squares, but we are adding, so sum of squares, there's no formula for that. So there's no formula for factoring sum of squares, so this one is done. This one is not factorable. So x squared plus 4 is not factorable. There's no GCF. There's no way to break down x squared plus 4. If you're tempted, this is one of the things that catches a lot of people. In a test situation, it's easy to think, oh, well, that must be x plus 2 squared. Isn't it just x plus 2 quantity squared? Well, no, because x plus 2 quantity squared is literally x plus 2 times x plus 2. That's what squared means. You have to multiply by itself. And yes, when you do first and last, you get x squared and you get the plus 4, but the outside-inside pieces of 2x and 2x give you an additional piece there of the 4x, x squared plus 4x plus 4, which is very different than just plain old x squared plus 4. So make sure you understand that x squared plus 4 does not factor to x plus 2 times x plus 2, because you would be missing out on that inner piece. So watch for that. Let's look at number 34. Again, boringly good here. The first thing we check for is there a GCF? Is there something that either letters or numbers both have in common? And in this case, yes. They both have a 3 that can divide into 3 and 15, and an x to the first. So when you undistribute that, you imagine dividing both terms by that GCF, by the monomial 3x. You're left with x squared plus 5. If we were to redistribute to check that, 3x times x squared is 3x cubed, 3x times 5 is 15x. So we've factored out the GCF of 3x, and now we ask ourselves how many terms are in the leftover piece. How many terms are in the leftover? Because that will tell us how we want to proceed in terms of factoring. In this case, sorry about that, got a little squished. There's 2 terms left over. In the case of 2 terms, you only have, it has to fit one of the situations. It has to be a difference of squares, a difference of cubes, or a sum of cubes to be factorable. In this case, you've got x squared plus 5. Notice I'm still bringing down the GCF to make sure it's part of my final answer. But in the x squared plus 5, you've got a sum. You do have a perfect square right here in the x squared, but 5 is not a square or a cube. And even if it was a square, there is no formula for sum of squares. There is no way to factor that. So this one is done. Can't be factored further. So your final answer is the 3x times the x squared plus 5. Make sure you do show that, because the GCF is a factor. When you want to factor something, you have to show that GCF. Okay, you can't just say it's not factorable just because part of it isn't. Just this second piece is not factorable any further, but it still was factorable from the beginning, 3x times the x squared plus 5.